Everyone in this day and age is rushing. We consider time to be the most valuable resource. But what exactly is time? Time has an inescapable influence on us and is driving us forward whether we like it or not, even though you cannot taste, touch, or feel it. Don't you always want to understand why time slows down as velocity increases and why shapes warp as they approach the speed of light? Welcome back to Theory of Science. I think time travel is real and I wish your enemy would time travel and become your partner. What do you say? If you don't want that to happen, then click the subscribe button. Time is an additional dimension. Before we add the 4D, we need to comprehend the 3D and their relationships. Height, width, and depth are commonly used to characterize three-dimensional space, and they all have 90-degree angles between them. Simply put, things in 3D space such as ourselves can move left and right, up and down, and both forward and backward. We are at ease in this environment. Using this as the foundation, we can better understand what we mean by 2D space and sometimes even 1D space. All we need to do is shift from one area to another is delete or add an extra dimension of measurement or motion that must be a 90-degree angle from all pre-existing angles. As a result, 2D things travel in only two directions in a plane, whereas 1D objects move in only one direction. Consider someone who lived in a 1D universe. All of the reality could exist to their left or right and would appear as a single dot. They couldn't move or see in any other directions, and they probably didn't ever know such directions even existed. Adding extra movement directions is now required to transition from 1D to 2D to 3D. In principle, we can forecast what we would need to do if we jumped to 4D. But then we reached a hitch. While drawing a line that is exactly perpendicular to a single other line or drawing another line on top of those lines that really is perpendicular to the two previous lines is simple, how can we draw a fourth line that is perpendicular to all three? Such a thing is obviously impossible. Such a thing is, of course, inconceivable in 3D space. The best attempt is to provide approximations. The lines in this illustration are all two-dimensional, but we look at them, our brains interpret them as a representation of a three-dimensional shape. In a similar manner, we could probably create a representation of what a four-dimensional object might resemble using only three-dimensional lines. This has been attempted by mathematicians, but their finding frequently leaves one perplexed. Glad to see you're still interested in this topic. We appreciate your time and would appreciate it even more if you could click that subscribe button and the bell icon. And if you like this video so far, then why not give us a big fat thumbs up? Thank you. Now let's get back to the video. There is some proof that the fourth direction exists and that we are currently traveling inside of it. Time is the fourth axis or dimension. When he combined space and time into a single space-time in his theories of relativity, Einstein foresaw this connection. Time and space, in his view, are two aspects of the same entity. This has a strong connection to 4D space because, just as there isn't much of a difference between the Z or the X or Y directions, there isn't much of a difference between time and space either if time is just another direction, even if it's one we can't see. Time is significant because, without it, our 3D space wouldn't move. It would remain in a single state because it's time that allows us to move around. Why though can't we see it? The XY plane, which we shall refer to as space, allows us to free up the Z dimension for the time by condensing everything in our current understanding of three-dimensional reality into a flat, two-dimensional area within this plane. In this paradigm, all 3D individuals are reduced to 2D. A 2D individual may exist and exist in the region denoted by the word space at the bottom of our diagram. However, they are also traveling through time because they're climbing the chart at a steady rate. We move through space more quickly than we move through time. One of the tenets of Einstein's theory of relativity is this. As our 2D individual tries to move left or right, our model can convey this idea through the strength of its vectors. While moving at a constant speed, their direction of motion alters. To move through time as quickly as possible, our 2D person must orientate his vector entirely in the future or upwards. The speed of casualty or the speed of light, to put it at its most extreme, would be implied by the fact that our individual has totally turned on its side and now only has movement in the direction of X and none in the direction of Z. They possess velocity in space, but not time. It becomes obvious that our 2D men have not gone through time at the same rate if our stick man on the right spins and vectors at close to its speed of light for a little while, then reorientates himself, while the second 2D man on the left simply remains where he is. Let's assume that our two stick figures are able to see each other. Imagine that they project a picture of themselves onto the other person's spacecraft and notice right away that they are different ages. The one who travelled at the speed of light did not progress through time as fast as the other, who remained stationary and is therefore older. Philosophers and scholars have been attempting to comprehend light since antiquity. In addition to attempting to determine its basic qualities, e.g. particle or wave, etc., they have attempted to make finite measurements of how quickly it travels. Scientists have been doing just that since the late 17th century and with growing accuracy. They have developed a greater knowledge of light's dynamics and the critical role it plays in physics, astronomy, and cosmology as a result. Simply put, light travels at amazing speeds and it's the fastest thing in the universe. Its speed is regarded as a constant and impenetrable barrier and is utilized to calculate distance. You may have observed how water rushes out of the nozzle and begins to fill up the tub if you take baths. It's entertaining to see the first waves of the water reach the bathtub's end and splash up alongside. Consider something even faster. What exactly are we discussing? Of course, light. Does light behave like a wave of water when you turn it on? Do you see it coming out of the light bulb and crashing against the walls like a wave? No. The room is instantly filled with light. It's impossibly fast. It's impossible to measure with your eyes. As previously stated, the flip of a light switch instantly fills a room with light. This identical occurrence was seen by early scientists. In reality, many early scientists believed that light did not travel at high speeds. Instead, they were thought it was either instantly present or not. Light movement is impossible to detect with the naked eye over short distances. Scientists would discover that huge distances were required to measure the speed of light. In 1676, Ole Romer was the first to demonstrate that light moves at a fixed speed rather than just instantly. He accomplished this by observing the apparent motion of Jupiter's moon, Io, which is hundreds of millions of miles away from Earth. In the study of physics and other sophisticated scientific subjects, the speed of light is an important constant. It also gives rise to an important astronomical measurement, the light year, which is defined as the distance light can travel in 1 year. The light from the sun arrives on Earth in roughly 8 minutes and 30 seconds. The light from our galaxy's next closest stars takes over 4 years to reach Earth. It could take billions of years for light to make the most distant stars in other galaxies to reach Earth. Several billions of light years separate the most distant galaxies. When scientists see light from faraway galaxies, they are actually seeing history, because what they see today does not always correspond to what those stars would look like today if you landed on one. This meant that the measured speed of light would simply be the sum of its speed through the medium plus the speed of the medium itself. However, Einstein's theory rendered the concept of motionless ether obsolete, revolutionizing the concepts of space and time. It not only advanced the theory that the speed of light is the same in all inertial reference frames, but it also presented the idea that as things move close to the speed of light, dramatic changes occur. These include a moving body's time-space frame appearing to slow down and compress in the direction of motion when measured in the observer's frame. If time is, in fact, a direction, this expands our knowledge of the cosmos and generates new issues. What drives us forward in time on an ongoing basis? Why does it seem that we can never move against it, even though there is no reason a vector couldn't do so in this model? Let us know your thoughts in the comment section below. Subscribe, like, and enable the bell icon for more interesting content, and check out other videos on our YouTube channel too. Thank you for joining us, and we'll see you in the next video.